All right, let's get started implementing depth-first traversal recursively. So first thing we need to do is define a function that accepts a starting node. Okay, so here I have the same graph we've been working with, has an adjacency list, vertex, add edge, remove edge, blah, blah, blah. Down here is the code I showed in the last video. If you want to set up the exact same graph as me, it looks like this, although it's not perfect, this diagram. We already have the nice slides. So what we want to do is come down here and just define, this is going to be very long. You might just want to go with DFS R and DFS I for recursive and iterative. But because this is my solution code, I want people to be able to find it and understand what it is very easily. So I prioritize legibility over length. So depth first, recursive, and it takes a vertex, a start point. I actually like calling this start to make that clearer. Okay, so that's the easy part. Now we have a couple things. We need to create a list to store the end result. We need to create an object to store the visited vertices. Okay, so let's do that. I'm gonna come down here and start off by making my, let's go with result first, an empty array. And then we'll also do visited as an empty object. Cool. So next up, we get to the meat of it. Create a helper function which accepts a vertex, and the helper function should return early if the vertex is empty. Let's just start there. So let's define the helper function. I'm just going to call mine DFS, and it takes a vertex. And then down at the bottom, I'm actually going to immediately invoke it with start, because that's the first time, even though there's no logic yet, the first time through, we want to start it off with start. You could also, you can define it this way, function DFS, blah, 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 and then call DFS manually and pass in start like that. But I prefer to do it this way. So function DFS vertex, and that vertex, we need to check if it's empty. That's our base case. So we'll just do if there's no vertex. And remember, that's when we hit the end of the line, if there's nothing to pass in to DFS. So if there's no vertex, we'll just return, I'll just return null. Okay, is this large enough? Hopefully. Okay, so here's our helper function. This will do the bulk of the work, adding data into result and visited. And then at the very end of this code, we'll return result when we're done. So let's start now with the real meat, which is we need to do this logic. The helper function should place the vertex it accepts into the visited object and push that vertex into the result array. Okay, so in here, we're going to add the vertex into result and add it into visited and set it equal to true is how I'm going to do it. So we'll do, let's visit it first. Visited of vertex equals true. So that's saying, visited A is true. And then also, we're going to do a result.push vertex. The order doesn't matter. So that's done. What's next? Loop over all of the values in the adjacency list for that vertex. If any of those values have not been visited, recursively invoke the helper function. Okay, well, I'll tell you right now, there's a small problem. We can write this sort of the simple way that you might think it should work. This dot adjacency list, referring to the graph, its adjacency list of vertex. So that should give us, like if we did A, it should give us an array B, comma, C. But let's just print that out. Let's do console.log this dot adjacency list of vertex. Okay, and I'm actually going to execute this code now and call it g.depth first recursive, pass in A. So we should just see that adjacency list, that array printed out, but we don't. We get this error. Cannot read property adjacency list if undefined. It's this lovely problem with this in JavaScript, the keyword this. So what I'm going to do to make this easier is up here, I'm going to define our adjacency list to equal this dot adjacency list, because in here, our context, the meaning of this has changed. So I'm going to preserve it up here and just call it adjacency list. Also, it makes our code shorter. So now if I do adjacency list, it knows when we say that we're referring to this dot adjacency list, where this refers to the actual graph itself. Rerun the code. Now we get B and C. Cool. Okay, so now instead of printing them out, we want to loop over it. So we're going to do a for each neighbor So I'll call it neighbor. Do the little fat arrow. We're going to check if that neighbor has already been visited. So how do we do that? Well, we have this visited object. We just pass in neighbor. So that will be, B and C for the first case if we're starting at A. And we want to do this if it's not been visited. If it has been visited, we can ignore it. But if it's not been visited, what do we want to do? If it hasn't been visited, recursively invoke the helper function with that vertex. Okay, so if it's not been visited, then we want to do return DFS neighbor. Okay, and we're basically done. We're missing one thing at the very end. I'm going to walk through this, of course, but we need to return the actual result array that we're building. Okay, so if this is, first of all, before I actually explain it, let me just make sure I implemented it correctly. It's very easy to have a typo when you're talking. Let's see. Moment of truth here. Okay, so G dot adjacent, nope, what am I doing? G dot depth first, recursive, starting from A. Okay, it's working. A, B, D, E, C, F. I've done this one a couple times, so I know that's the right order. I made the slides with that order. But let's actually walk through what's happening on the call stack. So if you're good just to see that it works and you're done, fair enough. It's a bit difficult to step through. But let's actually open up the debugger. And I'm going to call down here, just copy this line so we see what we're working with, and add a breakpoint. Okay, so if I execute the code, scroll back up to the exciting area, and I step through this. All right, we get our first call of depth first recursive where start is equal to A. And we initialize some of our data. Okay, now, then we get our first call, DFS with start. So vertex is A. So if not vertex, return null. That's not true, right? So we skip that line. We set visited of A to be true. We push A into result. Okay, so result now contains A. So we can scroll down. A has two neighbors, B and C. So we're going with whatever is listed first, which is B. That's the way that I constructed it. I added that connection before A to C. So we go to B first. So let's go to that part. You can see we get this anonymous function for the for each that's been added. And we're going to check, have we visited neighbor? Well, neighbor is B. We have not. So we return DFS of B. And you'll see another DFS in just a moment. Here we go. So we still have a couple calls here on the stack. This is DFS of A, our nested inner function here. This is the for each, which is waiting to also do for each of C. Okay, so now we're at B, and I'll speed this up a bit. We check, is there a vertex? Yes, vertex is B, so that line is not true. We make sure to mark B as visited. We push B into result. So now result has A, comma, B. Now, for each child, shouldn't say child, for each neighbor of B, which means B really only has one, which is D. And I actually misspoke. There are two neighbors. There's A and D, but we've already visited A. So you can see we're checking if we visited neighbor. Well, that's already been marked as visited. So this does not happen. We don't return DFS of A, but we try it again with neighbor set to D now. And this is true. We have not visited D. So we return DFS of D, and you'll see it added to the stack. There it is. This is DFS of D. Vertex is not empty. It's not falsy. So we keep going. We ignore that. Visited vertex is true. So now we visited D. We push D on, and we go to its neighbors. Well, what neighbors does D have? It has B, E, and F. So you'll see first time through, we're looking at B, but we've already visited it. So we ignore. Now we're looking at E, which we haven't visited. So we add DFS of E. Look at this call stack. It's growing quite a bit. DFS of E is up here. And we check if not vertex. All right, there is a vertex, it's E. So we mark it as visited. We push it onto result. Then we go to each of its neighbors. If we look at the adjacency list for E, you can see C, D, and F. All right, so we're going to start with C. It's listed first. And neighbor C, we have not visited C, so we return DFS of C, and it gets added on. Oh boy, I should have made a smaller graph. C, vertex is truthy, so we skip this. We visit it. We set it to be true in visited results.push C. Now for each of its neighbors. Well, what neighbors does C have? It has A and E. Well, we've already visited A, so we don't do this. We skip. We've already visited E as well, haven't we? Okay. So what happens now? This is the real moment. Finally, we've hit a dead end, right? We go to C, and we've been to A, we've been to E. So now what happens? Well, watch the call stack over here. Something got popped off. There was that for each that was waiting. So that's done. Now we're back here where we have vertex is E, and we're looking at its neighbors, which were C. And now we're looking at its other neighbor, which is D, which we've already visited. And now we're looking at its last neighbor, F, which we have not visited. So we're going to add DFS of F to the call stack. There you go. Now we're looking at F, and there is an F. We visit it, we add it to the results. Okay, now we look at each of its neighbors. Is there anything that has not been visited? At this point, we've seen everything. We visited everything on this entire graph. So all of them are marked visited, which means we're not returning anything here. So we keep going. And you'll see things get popped off eventually. And finally, we end up out of our inner helper function, and we're returning result at the very end, which looks like this. And then it should, just a moment. Almost there. There we go. A, B, D, E, C, F. Okay. So that was a lot to walk through. I totally understand if you didn't make it through that. I barely survived. So the recursion can be a little difficult to follow, but so just think of it as we visit a node and we visit one neighbor, and then we visit one of its neighbors, and we visit one of its neighbors. Anyway, it's a lot. Totally understand. I hope, though, that it at least makes a little bit of sense how it works, how the recursion works. Remember, I had to do this dot adjacency list. This is the one gotcha because the context, the meaning of this changed in our inner function. So I have to preserve it up here. Also, it shortens our code just a tiny bit. I expect there to be a healthy amount of questions on this one. This is a bit tricky, but I think it might also help in the next video. I'm going to do the same thing iteratively. So actually the order will be slightly different. It will still be depth first. There's not just one depth first order, but the actual result that we get will look a little bit different, and you'll see why in just a bit.